dust, empty skies, silence stretching across an alien world. A planet once visited only in dreams, now whispered in boardrooms, coded into blueprints, etched into launch pads. We once looked at Mars and wondered, are we alone? Today we ask, can we live there? Welcome to the Deep Dive. We're embarking on a journey today to explore humanity's Martian future. It's an ambitious look, really, at the science, the survival challenges, and, the very soul of a species reaching for the stars.
Yeah, and we'll be navigating this current push for Mars colonization. We want to cut through some of the hype, right? Give you a comprehensive, yet hopefully concise understanding of the scientific realities, the tech breakthroughs, and some of those deep ethical questions that are popping up.
Exactly. By the end of this deep dive, our aim is for you to be truly well-informed on this incredible unfolding story. It's happening fast. It really is. For decades, Mars was largely the realm of fiction.
Yeah.
Like Total Recall, The Martian. Now it feels different. It feels like a roadmap. So, okay, let's unpack this. Why Mars? And why this sudden surge of focus now, especially when we have, the moon right next door?
Well, that's a great starting point. A key takeaway from the sources we looked at is how Mars has genuinely transformed. It's shifted from like a distant science fiction dream into what feels like a tangible destination.
And why is that? What makes it tangible now?
A lot of it comes down to Mars offering some surprisingly Earth-like qualities, things that really set it apart from the moon as a place people could actually live long-term.
Like what?
Well, for starters, it shares a very similar day length to Earth, just over 24 hours, and it has seasons, much like Earth, because of its axial tilt. That might sound small, but psychologically and practically, having that familiar rhythm is a huge advantage for human settlers.
Okay, familiar rhythm, that makes sense. But what else?
Even more critically, our sources, like NASA reports and geological surveys, indicate vast potential for subsurface ice. Water ice.
Water, the big one.
Exactly. This isn't just a nice to have, it's absolutely crucial. From that ice, you can generate water for drinking and agriculture, you can produce breathable oxygen, and you can even synthesize rocket fuel right there on the planet.
Right, so that water ice and the elements you can get from it really sound like the game changer for actually staying there. For self-sufficiency.
Precisely. That's the key concept.
Could you elaborate a bit more on why Mars having things like carbon, nitrogen, hydrogen, and oxygen, especially in forms we can get at, like CO2 gas, nitrogen gas, that water ice makes such a fundamental difference compared to, say, the moon?
Yeah, absolutely. Mars is genuinely rich in these vital elements, often in forms that are, relatively speaking, accessible. Think about the sheer amount of water ice locked up in glaciers and permafrost. Some studies estimate that if all of it melted, the entire planet would be covered by an ocean over 100 meters deep.
Wow, that's a lot of water.
It's incredible potential. This availability is what makes Mars so promising for genuine self-sufficiency. It's a massive advantage for any long-term settlement. You're not constantly reliant on staggeringly expensive supply runs from Earth for basic survival needs.
Okay, contrast that with the moon then.
The moon, in stark contrast, is exceptionally dry. Bone dry, mostly. Its oxygen isn't floating around as gas or locked in easy-to-get water ice. It's tightly bound in mineral oxides, things like silicon dioxide in the rocks. Extracting that oxygen requires incredibly high energy processes, much more complex and energy intensive than splitting water ice.
So growing plants, for example.
Exactly. Growing plants on the moon at any scale would likely mean importing most of the necessary biomass, the carbon, the nitrogen, the hydrogen. Importing soil, basically. It makes true self-sufficiency there incredibly challenging, maybe almost impossible with current or near-future tech.
So while films like The Martian really captured the public imagination, showing someone surviving there,
Right, they did a great job with that.
but they often kind of gloss over just how monumentally difficult, how impossible maybe, this dream truly is without massive, almost revolutionary technological advancement.
They really do. The scale of the challenge is hard to overstate.
Okay, so forget the idea of beachfront Martian property anytime soon.
Definitely forget that.
Our sources make it crystal clear. You'll need a radiation shelter, a breathing tank just to step outside, and probably a whole lot of ingenuity simply to survive day to day. But let's get into the nitty-gritty. Imagine you just woke up on Mars. What are the immediate, undeniable physical barriers you'd face just by being there?
Well, the challenges are frankly monumental. The very first thing is the atmosphere, or lack thereof. It's incredibly thin, less than 1% of Earth's atmospheric pressure at the surface, and crucially, Mars lacks a strong global magnetosphere like Earth's, which means dangerous amounts of radiation constantly bombard the surface. We're talking two main kinds here: galactic cosmic rays, or GCRs, coming from deep space, and solar energetic particles, or SAPs, blasted out by the sun during solar flares.
And these are seriously harmful.
Extremely. Together, they pose significant cumulative cancer risks over time. There's also the risk of acute radiation sickness during intense solar events and potential genetic damage to humans. This isn't just needing sunscreen, it's a fundamental threat to life.
So how do you protect people? You can't just build a normal house.
Absolutely not. Protection demands sophisticated, multi-layered strategies. It essentially means humans would need to live underground most of the time.
Underground, like in caves or tunnels.
Or within heavily shielded surface habitats, domes perhaps. We're talking serious shielding. Sources, like NASA technical papers, suggest needing protection equivalent to roughly 15 centimeters of steel, or a full meter of rock, or maybe even 3 meters of water packed around the living quarters.
That's not just digging a basement. That's building a fortress just to have dinner safely.
Pretty much, a subsurface fortress.
Okay, radiation is a huge one. Then there's gravity. It's only about 38% of Earth's pull. We know about the immediate effects from astronauts in microgravity, muscle loss, bone density loss.
Right, we have a lot of data from the ISS on that.
But scientists are grappling with a much more profound question, aren't they? How will this lower gravity, 38%, impact multi-generational development? If people are born and grow up there, are we talking about a new kind of human physiology entirely? One potentially unable to ever return safely to Earth gravity?
That's the million-dollar question, maybe the trillion-dollar question. It's a crucial consideration, and honestly, the long-term effects of Martian gravity on human physiology are largely unknown. The multi-generational aspect you raise is perhaps the most profound unknown. We know that microgravity, from those long durations on the International Space Station and a one-way trip to Mars, is comparable in length, causes significant issues.
Like the puffy face and chicken leg syndrome.
Exactly, that's the classic description. Astronauts experience fluid shifts leading to that puffy face and significant muscle atrophy in their legs because they aren't working against gravity. They can also experience up to a 17% loss of blood plasma volume. And recovery from the bone demineralization and muscle atrophy after returning to Earth is a long, arduous process. For some aspects, it may never fully reverse.
So what does that mean for someone born on Mars? Or someone living there for decades?
We just don't know for sure. It's a genuine scientific frontier. Would their bodies adapt in ways that make Earth's gravity dangerous or even lethal? It's possible. It's a major ethical and practical concern for long-term settlement.
Okay, so on top of penetrating radiation and profoundly unknown long-term gravity effects, what other environmental hazards are lurking on Mars?
Well, you mentioned dust earlier, and that's a big one. Mars experiences colossal global dust storms. These aren't like dust storms on Earth. They can engulf the entire planet.
The whole planet.
The entire planet, yeah. They're common and can last for weeks, sometimes months, completely blocking out direct sunlight across vast regions.
Oh, what is that too?
We've seen these storms cause sustained surface temperature drops of around 4 degrees Celsius, and that cooling effect can linger for several months even after the storm clears. Obviously, such events would significantly impact solar power generation, which many mission plans rely on as a primary energy source.
Right, no sun, no power.
And it would severely interfere with communications with Earth, both visually and potentially through atmospheric interference. Not to mention the dust itself. It's incredibly fine, almost like talcum powder, and it gets everywhere. It can accumulate on sensitive equipment like seals and thermal radiators, causing them to malfunction. And crucially, Martian dust contains perchlorates.
Perchlorates, what are they?
They're a type of salt that's toxic to humans. Ingesting or even inhaling too much Martian dust could be a serious health hazard for colonists. So dust mitigation is a massive engineering challenge.
It sounds like a constant, relentless battle against the environment itself. So how do we even begin to mitigate these monumental challenges? How do we plan to build and actually sustain life there?
It really begins with innovative habitat design. The primary shelters, the places people will live and work, could be fixed structures, maybe partially buried for radiation shielding.
Or those underground fortresses you mentioned.
Or underground, yes. But they could also be mobile units, like pressurized rovers for exploration. All these habitats need to offer that pressurized volume for breathing, obviously, but also robust closed-loop life support systems. Think sophisticated air revitalization and water recycling, essentially acting as miniature, self-contained personal spaceships on the surface.
And how do you build them? Ship them flat-packed from Earth?
Some components, maybe initially. Engineers are definitely exploring modular and expandable designs. Things like inflatable habitats that pack down small for launch and then expand on Mars, or prefabricated modules like building blocks that can be shipped and shot, launched from Earth, and landed ready to connect together. The idea is easy, rapid expansion as a potential colony grows.
Okay, habitats. What about power? If solar is vulnerable to dust storms,
That's a major concern. While solar will likely play a role, especially early on, nuclear fission power is seen by many as a far more robust and consistent long-term solution. Small, compact nuclear reactors could provide steady power regardless of sunlight or weather.
nuclear on Mars. That's interesting. Any other energy sources?
People are also exploring geothermal energy, tapping into the planet's internal heat. But that requires a much better understanding of Martian geology, the actual heat flux coming from the interior, and very advanced drilling technology that doesn't exist yet for Mars. So that's more speculative for now.
And construction. You mentioned shipping things,
Yeah.
but building large structures, habitats, infrastructure.
Yeah.
It must be incredibly difficult and prohibitively expensive if you have to haul everything from Earth.
Right? Absolutely prohibitive. That's why in-situ resource utilization, or ISRU, is not just helpful, it's considered absolutely vital for any sustainable long-term presence.
ISRU using what's already there.
Exactly. The cost of launching mass from Earth to Mars is astronomical. So we have to learn to live off the land, so to speak. We need to use Martian resources to build, to breathe, to fuel our vehicles.
So what kind of Martian resources are we talking about for construction? Rocks?
Rocks, yes, the regolith, that loose surface material. But here's a really fascinating example highlighted in some recent research. Mars is surprisingly sulfur-rich. Its surface material averages about 2.48% sulfur by weight.
Sulfur. How does that help build things?
It allows for the potential production of sulfur concrete. You basically mix Martian regolith, say 50%, with molten sulfur, the other 50% let it cool, and it hardens into a strong, concrete-like material.
Sulfur concrete.
Yeah, and the key advantages are it's completely waterless, which is huge on a dry planet. It seems to be 3D printable, it's workable in the thin Martian atmosphere, and tests suggest it's surprisingly durable. Plus, producing it requires far less energy than making traditional Portland cement like we use on Earth.
So we're essentially designing entirely new construction methods tailored specifically to what Mars provides, making it possible to build large structures on site without shipping millions of tons of cement.
Precisely. That's the goal. And it's not just theory. NASA's Centennial Challenges program, for instance, has specifically incentivized research into 3D printing habitats using indigenous materials, simulated Martian regolith.
Any specific designs emerging from that?
One notable project mentioned in the sources is AI, Space Factory's Martia concept. It proposes a tall, cylindrical, maybe 4-story habitat. That shape is highly efficient as a pressure vessel holding breathable air inside against the near vacuum outside. And engineers think it's simpler for robotic 3D printers to build vertically, layer by layer, using something like that sulfur concrete or another Martian material.
Are there other Martian concrete ideas?
Yes, another interesting innovation comes from Penn State. They developed something called Marscrete TM. It's a type of dry geopolymer binder that uses minerals readily available in Martian soil. And crucially, it only requires a very small amount of water, which could be sourced from that Martian ice to activate it for printing. Again, minimizing reliance on water is key.
It's amazing ingenuity. It's not just about the materials, is it? It's about designing the structures differently, too.
Absolutely. The ingenuity extends to the structural design itself. Engineers are optimizing shapes to minimize tensile stress, that's the pulling apart force that traditional concrete is weak against, and maximize compression, the pushing together force, which concrete is very good at handling. This is ideal for the potentially more brittle concrete we might make on Mars. Optimizing the shape alone, according to some studies, could potentially reduce the amount of material needed and thus the energy costs by over 50%.
Incredible. Okay, so we have shielded habitats, maybe nuclear power, building with local sulfur or Marscrete. What about keeping people alive inside those habitats? Life support.
Right, the closed-loop life support systems. This is another area of intense research. One very promising avenue involves algae bioreactors.
Algae, like pond scum.
Essentially, yes, but highly controlled and optimized strains. These bioreactors can use sunlight or artificial light and the carbon dioxide exhaled by the colonists plus waste nutrients to grow algae. The algae, through photosynthesis, produce oxygen for breathing, consume CO2, and the biomass itself can be processed for food or other uses. It's a way to revitalize the air, recycle waste, and produce food all in one system.
A little ecosystem in a tank.
Pretty much. Genetic engineering is also playing a role, developing more resilient and efficient algae strains specifically for space conditions. The ultimate goal is truly closed-loop systems where nearly everything air, water, waste is recycled indefinitely with minimal input from Earth.
This whole thing sounds increasingly like a new space race. Maybe less overtly political than the first one, but definitely a race. We have NASA laying out these long-term visions.
Yes, NASA has its Artemis program, aiming for the moon first as a stepping stone, then Mars, targeting sometime in the 2030s for human missions.
Then you have China, with its increasingly assertive space program and plans.
Indeed. The China National Space Administration, CNSA, is also targeting Mars. They're often seen as the main government competitor to NASA. Their timeline seems to point towards human missions sometime after their current robotic exploration projects wrap up in the 2020s, maybe aiming for the 2030s as well.
And it's not just the US and China, right?
No, definitely not. The UAE, the United Arab Emirates, has made headlines with an incredibly ambitious goal, establishing a functional settlement on Mars by the year 2117. That's a long-term vision, but it shows the growing global interest.
And then there's Elon Musk. Constant stream of tweets, grand visions, and, well, Starship.
Ah, yes, SpaceX. It absolutely feels like a tacit race is underway. And the commercial players, especially SpaceX, are arguably driving a lot of the pace and public excitement right now.
Talk about Starship. It seems central to these more aggressive timelines.
It really is. Elon Musk's personal goal, stated since way back in 2007, has been to enable the human settlement of Mars. His motivation is often framed as making humanity multiplanetary for long-term survival, a sort of backup plan for consciousness. And Starship is the vehicle designed explicitly for that purpose. It's intended to be a fully reusable, super heavy lift launch vehicle.
Fully reusable. That's the key, isn't
It's
it?
the absolute key to drastically reducing launch costs. If you don't throw away the incredibly expensive rocket stages every time, the cost per launch plummets. SpaceX is aiming for eventual cost potentially as low as, say, $2 million per orbital launch with Starship, down from initial estimates around $10 million, which is already revolutionary compared to traditional expendable rockets costing hundreds of millions.
And Musk's vision isn't just planting a flag, is it?
Not at all. He talks about an audacious pace, aiming to eventually build one Starship spacecraft per day at the Star Factory facility in Texas. His ultimate stated goal is sending 1 million people to Mars, establishing actual cities, self-sustaining populations, even talking about having Martian mayors. It's planetary scale ambition.
1 million people. And their near-term plans.
SpaceX has stated plans to send as many as 5 uncrewed Starships to Mars in the next 2 years alone, primarily for cargo delivery and testing landing systems. That highlights just how aggressive their timeline is compared to government agencies.
Are there other commercial players seriously in this Mars game?
Yes, while SpaceX is arguably the most visible and aggressive right now, others have stated intentions. Boeing, a traditional aerospace giant, is involved with NASA's SLS rocket, which could play a role in Mars missions. And Jeff Bezos's Blue Origin is developing its own heavy-lift reusable rockets, New Glenn and eventually New Armstrong, and they've also stated long-term intentions for supporting missions to Mars. So there's definitely a growing commercial competition brewing.
It's just incredible to think that one, maybe a few, billionaires' ambitions could genuinely become humanity's interplanetary leap. But okay, beyond the race to get there, let's talk about the logistics of daily life and maybe a deeper question that starts to surface. Who owns Mars? The Outer Space Treaty from the 60s says no nation can claim sovereignty.
Right. The 1967 Outer Space Treaty is the foundational document for space law. It clearly prohibits nations from claiming ownership or sovereignty over celestial bodies like the moon or Mars. Space is supposed to be the province of all mankind.
But when people actually start moving in permanently, when companies like SpaceX are investing potentially trillions to build infrastructure and settlements, doesn't that fundamentally change the dynamic? The treaty feels a bit outdated for colonization.
It absolutely does raise new questions the treaty doesn't fully address. Establishing a permanent human presence, resource extraction, private property rights, governance for a Martian settlement, these are huge legal and ethical gray areas. While it's crucial that we ensure responsible exploration, avoid harmful contamination of potential Martian ecosystems, and act for the benefit of humanity, the existing framework for how an independent Martian society would function legally and politically is very much undefined.
What does property ownership even look like on another planet? Who decides the laws if it's not a nation? Can SpaceX declare its settlement independent?
These are the massive, complex, unanswered questions everyone is grappling with. There are proposals floating around ideas like planetary parks to preserve certain areas, designated economic zones, frameworks for resource sharing, maybe even eventual Martian self-rule. But none of this is agreed upon internationally. It's a huge challenge for the future.
And then there's the human element again. We talked about the physical challenges, but living on Mars, and that involves profound psychological hurdles too, doesn't it? Extreme isolation, confinement, the sheer distance from Earth.
The psychological toll is expected to be immense. Just think about the communication delay. Because of the distance and the speed of light, a radio signal can take anywhere from 4 minutes to 24 minutes to travel one way between Earth and Mars, depending on where the planets are in their orbits.
So a conversation could have up to a 48-minute round-trip lag.
Exactly. Real-time conversation is impossible. Real-time support from mission control or family back home is impossible. Imagine facing an emergency, a medical crisis, an equipment failure, and having to wait potentially 3/4 of an hour just to get a response from Earth. That creates an intense, unprecedented sense of isolation and self-reliance.
How are they planning to mitigate that? Besides just selecting very stable astronauts.
Mitigation strategies are a huge focus. Comprehensive psychological screening and training for astronauts is key, focusing on resilience, stress management, teamwork, and conflict resolution. They're also exploring technological solutions. Virtual reality, VR environments, could offer mental escapism, allowing colonists to visit simulated Earth locations or relaxing landscapes. And continuous telemedicine and remote psychological support, even with the delay, will be absolutely crucial for monitoring mental health and providing counseling.
It leads to that bigger question, though. You can put people on Mars, figure out the tech, maybe manage the psychology, but how do you actually create a society? A lasting, functioning community, especially without just exporting all of Earth's mistakes, our conflicts, our inequalities, and somehow expecting better results on a new world.
That's perhaps the core of the long-term societal challenge, isn't it? It's not just about the hardware, the rockets and habitats. It's about the software, the people, the culture, the governance. It really demands thinking about a new kind of social contract, perhaps from the ground up. It's a daunting but fascinating prospect.
Shifting gears slightly, but related to daily life there. Living on Mars won't just be about surviving the environment. It'll inevitably be about evolving how we live, deeply integrated with technology. How might something like artificial intelligence, AI, transform daily life on the red planet?
AI is expected to play a truly crucial, indispensable role from day one. We're talking about highly autonomous systems handling tasks that are dangerous, tedious, or require constant monitoring. Think autonomous rovers for surface transportation, tirelessly mapping terrain, exploring geological sites, moving cargo and construction materials without needing a human driver for every meter.
And beyond driving.
Medical bots, AI-powered diagnostic systems, maybe even robotic surgical assistants, will be essential given the communication delay making real-time consultation with Earth surgeons impossible. Remote labs, also driven by AI, could perform complex scientific analyses on Martian samples without constant human supervision, extending the reach and efficiency of research.
What about managing the colony itself? Communications.
AI will be critical there too. Managing the complex life support systems, power grids, and especially the communication systems. You'd likely have autonomous satellite operation for the network around Mars and the relays back to Earth. AI could handle real-time data processing, optimizing bandwidth usage, maybe even predicting and mitigating communication dropouts. It's about making the whole infrastructure function more reliably and efficiently with minimal human intervention needed for the basics.
And for the colonists themselves, walking around outside those habitats, how will their immediate interface with the environment and technology change? What might daily life actually feel like during an EVA, an extravehicular activity?
Well, the spacesuits themselves will become far more advanced than the Apollo or even current ISS suits. They'll essentially act as true personal spaceships. They won't just provide pressure and oxygen. They'll be integrated systems protecting astronauts from radiation and dust, providing heating and cooling, monitoring vital signs constantly, and offering sophisticated communication and navigation interfaces, maybe augmented reality displays inside the helmet.
So the suit is your world when you're outside.
Absolutely. And communications back to Earth, while delayed, will likely be much higher bandwidth than in the past. Systems using lasers rather than just radio waves could potentially send massive amounts of near real-time information, including high-definition images and video feeds, back to scientists and the public on Earth.
Ultimately, beyond the tech and the survival, what are the big questions this whole endeavor aims to answer about Mars itself?
That's the fundamental scientific drive, isn't it? The goals are profound. Was Mars ever home to microbial life in its warmer, wetter past? Is there perhaps still microbial life hiding beneath the surface today? Could Mars truly become a safe, long-term second home for humans? And perhaps most importantly, what can studying Mars, its history, its climate change, its potential for life, teach us about Earth's own past, its future, and maybe about the potential for life elsewhere in the vastness of the cosmos?
Big questions. Okay, let's pivot to the perhaps more pragmatic side. Mars may be the red planet, but the money is undeniably what fuels this incredibly expensive journey. What's the economic case here, beyond pure scientific discovery and national prestige?
That's right. Perhaps the major obstacle to large-scale Martian colonization is the staggering mission cost. We're talking numbers that dwarf previous space projects. Estimates suggest a human Mars mission architecture requiring maybe 900 to 1,300 metric tons of hardware delivered to low Earth orbit just to get started could cost somewhere in the range of $320 billion to $460 billion.
Billion with a B.
With a BU. And just the advanced life support systems needed for that crew could cost around $2 billion on their own. For perspective, the entire International Space Station, built collaboratively over decades by multiple countries, cost somewhere around $150 to $160 billion in today's money. So a Mars mission is potentially several times more expensive than the ISS. The scale of investment is just immense.
So, how on Earth or how on Mars do you make that kind of undertaking economically feasible? Is it really possible to make it pay for itself? Or are we just talking about massively expensive, government-funded expeditions for the foreseeable future?
This is precisely where in-situ resource utilization, ISRU, becomes the absolute cornerstone of any economic viability argument. We talked about it for construction, but it applies across the board. Using Martian resources, water ice for water and air, regolith for building, atmospheric CO2 for fuel synthesis, significantly reduces the amount of mass you have to launch from Earth. And launch costs are the biggest driver of mission expense.
Less mass launched equals lower cost.
Dramatically lower cost. While setting up ISRU capabilities, the mining equipment, the processing plants involve significant initial investment and ongoing operational expenses and maintenance. These costs are projected to be far, far less than shipping literally everything, including water, air, and fuel, across tens of millions of kilometers of interplanetary space. The less you have to bring from Earth, the more feasible the whole enterprise becomes.
Okay, so ISRU makes staying there cheaper. But are there resources on Mars that could be valuable enough to justify extraction and maybe even eventually sending them back to Earth or using them for other space activities? Could Mars actually become profitable?
That's the long-term economic question. And there are a few intriguing possibilities that could drive significant economic activity, though some are more speculative than others. One confirmed resource advantage Mars has is deuterium. That's heavy hydrogen, an isotope crucial for the nuclear power industry today and potentially essential for future fusion reactors.
And Mars has more of it.
Significantly more, proportionally. Deuterium makes up about 833 out of every million hydrogen atoms in Martian water, compared to only about 166 per million in Earth's water. That's roughly 5 times the concentration.
Yeah.
Deuterium is currently valued at around $10,000 per kilogram, so potentially millions, maybe even billions of dollars worth of deuterium could be produced relatively easily as a byproduct of the water electrolysis that colonists would already be doing to get hydrogen for fuel and oxygen for breathing and plastics production on Mars.
So a valuable byproduct of necessary activities. What else? Minerals, precious metals.
That's more hypothetical right now. Mars has a complex geologic history different from Earth's, involving volcanism and water activity. This suggests the possibility of concentrated ores of various metals, maybe including precious metals like platinum group elements. Some speculate these deposits might be more accessible near the surface than Earth's increasingly depleted reserves. But finding and verifying economically viable ore bodies requires extensive geological surveying that hasn't happened yet. It's a potential long-term driver, but still speculative.
What about looking beyond Mars itself?
That's another key potential economic driver: Mars's proximity to the asteroid belt. Launching mining missions to resource-rich asteroids might be considerably cheaper and require less energy starting from Mars's lower gravity, well, compared to launching from Earth. Mars could become a logistical hub, a sort of gas station and base camp for accessing the resources of the asteroid belt. That could be a very powerful long-term economic incentive.
Okay, so beyond digging things up or using Mars as a base, what other private sector incentives are there? What might spur investment and innovation in building a Martian future besides government contracts?
There are definitely powerful indirect incentives. A big one is technology transfer back to Earth, developing solutions for extreme environments like Mars. Think ultra-efficient water recycling, closed-loop agriculture, advanced robotics. Novel construction methods like that Martian concrete could lead to breakthroughs that benefit sustainability and quality of life right here on Earth. Maybe Martian building techniques influence affordable, sustainable housing designs.
So innovation driven by necessity.
Exactly. Then there are things like inducement prizes. NASA's Centennial Challenges are a good example, which motivate private companies and research groups to develop specific technologies by offering significant cash prizes. And of course, just the sheer potential for the development of entirely new supply chains, new industries, and new markets, both in space between Earth, the Moon, and Mars, and also spinning off into terrestrial applications, creates immense long-term economic opportunities that attract investors looking for the next big thing. It's not just about what Mars has, but about the economic ecosystem the journey itself creates.
We've covered a lot of ground, the science, the immense challenges, the global players racing there, the staggering economics involved. But it feels like the biggest question still kind of hangs in the air. Fundamentally, why? Why do we seem to yearn for Mars? Is it purely about wonder and exploration? Or is there something else driving it, like escapism?
That's a deep question, and the motivations are complex and debated. The quest for Mars colonization is indeed seen and explicitly stated by some proponents like Musk as creating a plan B for civilization, offering a potential refuge, a second outpost for humanity against catastrophic global threats that could arise on Earth. Think a large asteroid impact, runaway climate change, nuclear war, even a super pandemic, ensuring the long-term continuation of human culture, knowledge, consciousness
A
itself.
lifeboat for humanity.
That's one framing. But this immediately raises an important and very difficult ethical question for all of us. Considering Earth's own immense pressing challenges right now, the climate crisis, rampant global inequality, persistent wars and conflicts, is it truly noble to be spending hundreds of billions, potentially trillions of dollars to establish a small, fragile colony on Mars? Or is it, in some ways, profoundly negligent?
It really does force us to look in the mirror, doesn't it? The argument goes, if we possess the technology, the wealth, the ingenuity to potentially terraform parts of Mars, or at least build sustainable habitats there, then shouldn't we be applying that same level of resources and commitment to fixing the problems right here on our home planet first? Why not regreen the Amazon, or lift billions out of poverty, or transition fully to sustainable energy? Is it somehow easier psychologically to dream of abandoning the house than fixing the leaking roof?
That's the crux of the ethical debate. There's no easy answer. Proponents argue that the drive to explore and expand is inherent to human nature, that the technological challenges spur innovation benefiting everyone, and that becoming multiplanetary is a necessary long-term survival strategy. Critics argue it's a dangerous distraction, a misuse of vital resources, and perhaps even an abdication of our responsibility to care for the only home we have ever known. It forces a fundamental conversation about our priorities as a species.
So in the end, Mars isn't just a destination.
No. I think Mars is not really a backup planet. In many ways, it's a mirror. It reflects our greatest hopes, our highest ambitions, our incredible technological prowess. But it also reflects potentially our arrogance, our tendency to run from problems rather than solve them, to actually attempt to colonize it, to build a society there. It's perhaps the ultimate test of what kind of species we really are. Are we just smart enough to physically reach the stars? Or are we wise enough to carry our conscience, our ethics, our best selves along for the ride?
A powerful thought to end on. Thank you for taking this deep dive with us today. Stay curious, stay grounded, and stay tuned for the next one.